So let's start. Last time we were here, and I think I just stopped here asking you. Suppose if an object is connected to the base frame through two springs or two sheet flexures, so each will constrain 3 degrees of freedom, right? So by now you understand that each sheet flexure will it will provide 3 constants, right? So another 3 constants. So total 6, right? So if we add total 6 constants, so and if it's exactly constraint design, or suppose if we want to constrain it kinematically and we put 6 constraints, then we may be able to constrain it completely, right? So the question is whether it's possible with the two leaf spring or two sheet flexures. So I'd like to hear from you. Just switch on your mic and you can answer me. Just we can stop for a while and just let me know if it's possible. Or do you think there will be still some degrees of freedom left? And yes, maybe certain degrees of freedom or certain directions are constrained twice, or maybe more than one time. So what is your observation? Anybody?
So translation, Z direction,
Sorry?
translation along perpendicular direction.
So which perpendicular direction? So I
Um,
can put a frame. So suppose this is X and this is Y and
along Z,
this is,
along Z.
so if I write X, Y, Z, right? So which one you think that might be possible
So translation along Z axis.
along Z axis? Okay, anybody else?
So rotation about x-axis.
So translation Z, rotation about X.
Yes.
Yes. Any more answers? Anyone to make any correction? So what happens if you consider the sheet flexure 1? What will be the constraint direction? Of course, it's in plane X and Y, right? Those are constrained. X, Y, and the rotation along Z, that will be constrained, right? So if you consider this plane, this sheet flexure, and this is the rotation. These are constraints, right? Three constraints, right? If you take 2, again along the X, so if it's along the, assuming that is along the plane, right? Along Z translation and rotation about Y, right? So total 3 plus 3 6. So it's in parallel, so constraint can be added, provided they are not constraining the same axis. So if they are constraining the same axis, maybe then it might be difficult to constrain one of them. So what is missing? If you see here, if I check overall, x direction is constrained by this x translation. So twice, right? So if I say x direction, two times translation, right? Y translation, yes, it's constrained once. So it's constrained once by this. Z direction is constrained translation constrained once. What about the rotation? X rotation, I don't see any, right? Either one or two is not constrained. So actually the rotation is not constrained along X. Y, okay, is constrained once. Z is constrained once. So what do we find here? That the rotation is constrained twice, translation along X is constrained twice, and it appears that the rotation along X in the same direction is not constrained at all. So translation Z may not be true, right? Why? Because if you want to translate along the direction, actually the sheet flexure 2 will constrain that motion. Okay. So rotation X is I think is correct. So what we can say now that this translation is constrained twice, and rotation is free along this direction, right? So because 3 plus 3 6, but one of the translation is constrained twice, so it's over constrained. So X direction, if we talk about what we see that the both of the flexures actually constraining that translation, and because of that 6 minus 1, so it's constraining only 5. So 1 is still left, and that 1 is the rotation along the same direction. And if you check carefully, what do you observe? If you extend the two planes, two surfaces, actually they intersect. They intersect at that line. So it's a line of intersection of the two sheet flexure. So actually, if you take that line and try to rotate, actually both can rotate because this outplane rotation we are talking about. So it can rotate, and this can also rotate. So none of them will constrain that rotation. Translation, if you talk about, yes, both are getting constrained. So now if you at the center, if you consider, and suppose if you just put a suppose a frame of reference, you can very much see that what are the motions, right? So if it's over constrained, then if the number is 6 or whatever is the number, but if by adding you what number you get, number of constraint, it will get reduced, and so you'll have more number of degrees of freedom left. So in this case, it's supposed to be 6, but 1 will be always left. So no matter how you put two flexures, these two sheet flexures, there will be always a intersection. So two surfaces will intersect somewhere, and translation along that line is over constrained. So it's a constraint twice, and the rotation is available. So the rotational degree of freedom is here. So you can try, and it can be an open question for you. So try different orientation, and you will see there is always one degree of left. It will not constrain all 6. So I think you try different cases, and maybe we can discuss in coming lectures or in even in lab sessions. So over constraint means also there might be some issues. So like talking about the translation. So put like this, the translation degree of freedom along this direction. So uh, which one will which one actually constrains? So actually they will fight, both of them, 1 and 2 will fight, right? So moment you start clamping, you realize that one of you have to adjust clamp one, the other one you have to leave free, and once assembled then only you clamp it. But if you clamp it little bit more, then you start observing that they will start fighting with each other. So then the stiffness will cover. So here we are talking about the rigid bodies. So that will be a problem. So maybe if it's a somebody purist and want to design exact constraint design, then they will try to get rid of one of them. And how you can do is by replacing one of this with the flexure, sheet hole flexure, because here, so here you have, so if I uh, just put the direction, talking about translation and rotation. So this one will provide 3 constraints, but this one will provide only 2 constraints. So 3 constraints here, and here 2 constraints. And if you look closely, this will constrain the translation along this direction and the translation along this direction. So it will provide only 2 translations. These two translational constraint at the hinge. The rotational constraint will be free. So what you will also observe that the nature of constraint will change as you move the point of observation. So if you are observing from different points, the rotation may become a translation, or translation become maybe a rotational constraint, and vice versa. So I think that this will be clear to you. Now we'll talk about some of the examples, some of the implementation of the concepts what we have studied. So there are various ways of controlling degrees of freedom, and how we can use it in day-to-day design problems. So for instance, one of the cases like what happens if you want to support a spherical ball. So if you want to create a ball joint, usually what you do, suppose this is the stem with the spherical ball. So on the other side, what you want to usually do, and most of the time people will do, is they will try to create a conformal surface. So a spherical hole to receive that spherical ball. And if you want to go for precision, then that has to be exact, right? The radius, the sphericity, or whatever you call it. So you don't want any change. So if you go for conformal one, then the same surface want, right? But you know that in reality it's not possible. There will be always error, and because of those errors there will be some uncertainties. So there will be compromise between the accuracy you can receive or precision you can receive based on the manufacturing tolerances. So and of course if you go for very high precision, then you go for very like a lot of machining process, and maybe very precision machining processes. So like if you have to get this, then okay, you go for grinding, ribbing, reaming, then spark machining, and even later you also rely on some plastic deformation. So you also assume that when once it's sitting on the hole, you also assume that there will be some plastic deformation and it will completely fit there. But of course, the problem will be also in terms of performance because of the friction. They are contacting surfaces. So there will be a lot of issues, right? So one is like the complete surface. So you want to graph from the entire surface, right? Okay, of course, many times at the bottom you want a hole because, okay, if the air is trapped, then maybe it will not receive it properly. Sometimes you may have to find a way to provide a nesting force from the top, so you may cover it with another sleeve. Uh, Sometimes what you do, like you only create a partial surface, right? Again, it's not easy because it's you have to follow different processes, right? And it will be costly affair, right? But if we look closely, what we realize that this is not required, right? This is complete surface. Then you go for partial, right? So you are using this surface, a spherical surface. But you know what you want is a spherical joint. So what you need is maybe just 3-point contact. So what you go for? Three surfaces, three bearing surfaces, right? And okay, it can be a spherical, but I think slowly you may realize that you may not need any spherical surface as well. It can be simply a flat also. So just three flats from three sides, right? Three flats. So maybe try to make, and okay, we'll make three contact at these 3 points, and it will be centered, right? And, this is what we learned. So many people can argue, and people who have not worked with this kind of things, they will say, oh, this will not be good and this is not going to work. But you can do the mathematics and you can clearly show that it's good enough and it's as good as any perfect spherical surface what you have in the first case, right? So this is one of the examples. So moment you have to create any spherical joint, you don't have to create a spherical hole also. You can have a spherical ball, but it can be simply supported on three surfaces. And the intersection point will give you the center of rotation, this point, right? So simple, right? Okay, of course, then you'll have an issue with the friction. So friction you can get rid of because using some flexure joints. So there are other things. So there is this slotted hole, and you can use that one, and you can clamp it. So there are different ways. But still, you find that friction will be one of the issue here. Friction. So you can even go for. So one is like with the three contact point, but because of the physical contact and because of there will be some uncertainties and maybe difficult to control. So then if you go for even higher precision, then you go for flexure design. And flexure design is something like, again, along the three constraint line, what you can do is you can simply use, so the three constraint lines, right? And along the constraint line, you simply use wire flexures, right? So the wire flexure, yes, here the problem will be they will not be intersecting because, okay, if they intersect, then they all have to be welded, and then it may not work the way you designed it. So okay, there will be offset, but it's still, I think it's deterministic and you can find it. Of course, what you have to understand here is the points here, the 3 points, they are not intersecting here, the middle points, and they are moving also, but very much they are deterministic, and you can calculate beforehand how much they will deviate, and you can always compensate for that. What is good about it is you don't have a hysteresis, because if you apply a force, there will be deflection. So it's always F equal to Kx. So there will be some deformation, and it will be completely governed by this stiffness. So there will be some stiffness, and there is always one-to-one correspondence. Hysteresis is something like you don't know where you are, right? And that's the, whenever you have a option involved, you will have a dead band, and you are sure where you are. So that's one example. The very common example is the design of a coupling. So suppose if you are, so this is shaft, one shaft, and this is the second shaft, right? And you may need to transfer the rotational degree of freedom, or only want to transfer. No, I won't say the rotational degree of freedom, but I take you want to transfer the rotation part or the torque, whatever torque is there, you want to transfer to the shaft 2, right? But these two shafts can't be aligned perfectly. There means, and it's a tough job if you really want to. So if you, because ideally they have to be collinear, right? But again, because of assembly issues, because of the machining issues, there will be always some offset, radial offset, and some misalignment. So think about these two problems. So radial offset is like two axes having this delta. Misalignment is like one is going like this and one is going like this, right? So this one, there will be always. So of course it's exaggerated, but there will be always some offset and misalignment, right? And smaller you want to make it, higher will be the cost. Okay. But how you can get rid of this problem, or how you can design the coupling so that it will take care of this radial offset and as well as the misalignment, but it still is able to transfer all the load, whatever forces you have along along the longitudinal axis of 1 to the 2. The torque transmission, it will happen perfectly, or the rotational. So whatever rotation you have, so if it rotates by theta, it should rotate by theta or plus minus whatever, but there is a one-to-one correspondence, right? So what you, in this case, if you are just talking about the coupling, requirement is one constraint device. It should provide only one constraint, and that constraint is the rotational constraint from shaft A to shaft B, from member 1 to member 2, right? And it should provide rotational constraints. So whenever the question is asked and it's asking transferring one off a rotation, right? And what does it mean? It should provide one constraint only. All five should be, there should be 5 degrees of freedom, so that it can take care of this radial offset and misalignment in whatever direction you have, or even the distance between the two shafts when it's in motion. So try to visualize that. But the primary requirement for coupling is to transfer this one off, and that is the rotation. So in principle, how you can do? So you are talking about the rotation, but if you just move it from that axis of rotation, it's equivalent to a translation constraint. And if it's a translation constraint, what it means that it's possible to constrain it just by a pin or a bar, or even a wire, right? And that's the beauty. So try to visualize that. What we are claiming that if you look from the side and suppose you connect two flanges, flange 1 or flange 2, so there is a angular gap. So it's just perpendicularly protruding out, and then okay, you just put a flange, and then you try to out of the paper here this pin and connect them, right? So now what you can see is this is providing translational constraint. Translational constraint along the tangential direction. And if it provides that tangential constraint, the rotation at this point, this axis, will constraint. Because as long as this is constrained, the translation is constrained at this point, the rotation is also constrained. With respect to each other, cannot rotate. So I think just try to visualize, and so whatever examples I'm showing you here, I will ask you to just quickly make a CAD model of it and try to visualize. It's very easy, and you can see it yourself, right? So in principle, a wire flexure will be good enough to provide the constraint what you want from a coupling. So coupling with a single thin bar, right? Of course, talking about the stiffness, so it's dependent on this A and radial displacement and the stiffness of the wire. So this is a rotational stiffness. And when you are talking about angular precision, you can also talk about that, and that depends on eccentricity, this E value. So if it's not radially there, right, or whatever is the offset here at this point in the shafts. So it's all trigonometry, and I think you should be able to calculate it. So what is the catch here is it should be perpendicular, right, and out to that. Even if it's like this, it will work. But if it's close to a radial one, it may not be able to work, right? Because what you want is there should be a equivalent constraint along this direction, then only it will work. So suppose you want to design a flexure coupling, and you want to have want to distribute it, because it may not be dynamical, because it's only offset to one direction. So you can make a very symmetric design here and can create a kind of universal joint. So what you do, you take a disc, so one disc here, green one, and another disc, right? And then you connect through the bars. You see here, so you connect them through this. So, but what you have to ensure is they should not pass the center, right? So it's here. So this is your effective moment, right? So there should be a radial distance. So three wires will provide you the coupling stiffness, you can call it, or even the required constraint in the rotational direction. So you try to visualize, you just try to rotate one with respect to other. So two, and try to rotate one, and try to visualize how it will transfer to the other member. because then it will try to move these bodies, right? And they are stiff in this direction, and that's how it will transfer the torque or the rotation to the other member. But any other motion, right, or you try to move or try to bend, is possible because it can easily flex, because it's just like a cantilever. So cantilever simply and clamped at both ends, right? So you can just think of two bars and clamped rigidly, right? So you try to move and you can, but you try to move along this direction, it's not possible, right? So this is the constraint. You can further, you can design two universal joints, 1 and 2. So you can take a drum kind of thing, and then you arrange it, and you can, so it's just like you have one shaft, and then you have another shaft, and then you have one shaft. So I think in kinematics you always just study about this kind of setup. So two universal joints use, so it can rotate out of the plane easily. But the rotation can get transferred easily. Rotation and this one. Very good example is Oldham Coupling. So if you don't know, please revisit your machine design or machine design of machine elements. So in coupling, very popular coupling is Oldham Coupling, and this concept. So theta phi in, phi out, and this is how it works. So you have intermediate member, and it has a slot in perpendicular direction, so it can slide and it can provide the rotation. The rotational constraint is always there. But of course, they are all moving members, and they have physical contact and a lot of friction involved. So for a heavy application, for not so precise application, use it, but immediately you can convert it, and you can use the, because in principle all coupling is designed based on the kinematic uh, constraint requirements, and you just have one constraint, rotational constraint. So if you want to convert, very much you can convert using flexures. And what you have here, but you see the red part is basically like there are 4 wire flexures. So it's just one sheet metal, right? Thin sheet metal. You take very thin sheet metal. The section here, the T is just this T, right? So if you take a thin sheet and cut it, saw it. So from this point to this point, you see 4 of them. So earlier you have 3, here you have 4. But the way they are connected, actually they are making just, they are connected through these 4 wire flexure. And now you realize that it's so easy. You don't need so many components here. If you start counting the number of components and moving parts, there are many. Here you can just use a sheet metal, maybe depending on the application. And suppose it's a heavy application, you can go for 2 to 3 millimeter thick sheet metal. If it's not a heavy application, you can even go for 0.5 or 0.3 sheet metal, and you cut it, and you can observe that they are really good, and they can provide the constraint required. So I'll ask you to just so this is also called Costa Coupling, under the name of the Dutch professor Costa. So very simple, and I would like you to develop the CAD model of these, and then we can make ourselves, at least we can do the 3D printing of these things and can get fabricated. So this one you can do and we can try. Okay. Another version is out of sheet metals. So what essentially you are doing is the two shafts are like just out of the plane, right? One is like this side, on other is on the other side. And what you see, this wire flexure are nothing but these are the constraint lines. But these constraint lines can be replaced by this wire flexure, but they can be also converted by folded leaf springs, right? So these are folded springs, just like this. So you see these are the folds, and where are the two sections? So you see this is one section and another is this section. You cut the groove, right? And this is clamp. So the very nice design, very creative, I would say. It's just made of one sheet metal again. You can see here the first part, and you just cut it and then bend it now. So one side bend to this direction, other one this side bend to other direction. So you can see this bends, right? And that bend like connected to one adapter here, and this side connected to this adapter here. Yeah, and then can be locked to one shaft here and locked to the other shaft. Very simple, and it can be very robust. So this you can try, and I can also see yourself. So the torsionally very stiff coupling based on folded sheet flexures. So you can use them to design. So though we are saying coupling, and coupling is a very loose term, I would say, and many times uh, people from electrical and other, they say, oh, you just want to connect the motor to the shaft. It's just, it's not simply connecting two mechanical elements, but connecting them properly so that you get the precise motion, right? That's the idea. And if you want to connect two components and want to have that rotational constraint, wherever you have that kind of requirement, you can use this concept. Coupling is okay, it's very much used in sense, and that's why you always say coupling, but it's just one constraint, rotational, providing one rotational constraint. What are the other ways, right? So here, suppose if you want to constrain the rotation part, you can also use again a sheet metal here and another sheet metal here, right? And then you have a torsionally stiff member at the center, right? And okay, through this you can connect them. But what you have realized that this looks very asymmetric design. But what happens? Suppose this blue one, you just make it bigger and make it concentric, then it's nothing but it's like this part. So concentric drum now, and then the rate become diaphragm, and then you get this design. So this is suitable for high rotational velocity because it's a symmetric design. And in case of high rotational velocity, you also talk about the eccentricity, you talk about the imbalance, right? So here the imbalance can be minimized. So you can see how conveniently it can be designed, and you can see the notches here. These are also providing you the compliance, necessary compliance, right? But the tube is rotationally stiff. So diaphragm will provide a kind of U motion. So the two rotation and the two rotation at the other end. So you will get very good design out of the tube also, and the two diaphragms. Let's stop here, and we'll continue discuss about this. And one thing what you realize here is using these principles, the constraint lines or the using the flexures, so-called, in this case, just remove the constraint line with the wire flexures. And what you can design is something which is like, suppose if you have a very sensitive set of equipments or object which you want to constrain and provide certain degrees of freedom only, but don't have a place to hold it, right? So then remotely also you can design these kind of structures. So that's why all these structures, all these things you are designed, you have to visualize them as the mechanisms to provide required constraints. And the moment you start thinking your support system or your structures as mechanisms, then it will be a lot of fun. And that's the basis of these courses. And many times we talk about kinetostatics. And so kinematics and statics, there are some duality, and we talk about that. So very interesting, and those things are covered usually in the higher courses, in advanced courses of mechanisms, or so. Actually, these two fields we try to merge and try to learn from each other. So there are a lot of there is a wealth of knowledge already developed, but how to put them together so that we can get this structure or mechanism and can design this precise equipment or precise devices, I would say. So that's the idea. So in this case, suppose you want to constrain axial displacement without using material at the center line, right? Suppose this is the rod or pin or bar, you call it. But at the center, you don't have any way to put anything there. Or maybe you want to place something else there, right? But you still want to constrain the displacement, X displacement only, right? How to do that? And what you see here is you have the base A, then you have the intermediate H, and then you have this. You are talking about point M, right? What you see here is again, it's a serial connection. You see from A to H to the, so suppose call it P, I would say P. So this is the object, and this is the point of interest or the object, and maybe you are talking about this translation Z only, Z translation, so thick line. So this is the axial constraint you want along Z. All other you want to get it constraint. What do you see here? The base is a fixed base, right? So what do you see? X, Y, Z translation, phi, psi, theta, all the three rotations. It's a rigid, right? So it's a rigidly clamped. So of course you have all the 6 DOF constraints. I think 6 constraints here. You all agree, right? Now what happened? You have this wire flexure 1, 2, 3. So 3 wire flexure provide three constraint, right? 3 constraint, but what is the degrees of freedom they provide? They are only constraining 3, so they will release 3 degrees of freedom, right? So from board A to H, if you see 3 degree of freedom released, 3 or I would say 3 constraint release. So you are left with now 3C. And what are they? So if you talk about H with respect to A, the Z translation is still there, right? And this 2 rotation out of the plane, or the plane rotation, I would say, out of plane. So along X and Y rotation you cannot have. So these are like three point contact, right? So you are all agree. So you are left with three constraints. Now again, now this object, the conical shape, now connected with 1, 2, 3. Another three constraints, so 3 DOF released, right? But it's not happening. What you have is one constraint is still there, right? So of course, then you can say that there will be over constraint. And what happens if it's in series? Then whatever constraint you want, you have to keep constraining. So jet translation, what you observe, that it's always getting constrained from A to H, from A to P. When you come, jet translation again constraint, right? But what happens in this case, these two air flexures are intersecting at point M. So what happens, this point M is constrained completely. So the translation, right? And but they're already released elsewhere, right? So what happens from H to P? So this phi and psi, if we talk about, they are released here, right? Z is still constant. So if you talk about this point M, what you realize that only constant is this translation, right? So P with respect to H, it will have three constraints, agreed. But I move from H to A, and they are in series, and that's why it's a little bit tricky, because when it's in parallel, you can add the constraint. But if it's in series, you add the degrees of freedom. So here, like from A to H, it's a 3 DOF. H to P, again 3 DOF. So you can say 3 plus 3, 6, right? So all 6 DOF should be there, but that's not true, because the jet translation is still constrained, just like two sheet flex case. So it's a still constraint, and that's why you still have constraint there. So in series combination, it should be AND. It should be constrained by at both the places. Then only it will be constrained. If it's released once, it will be released by them. So, and what is good about this is now you can realize that along this line there is no material, but still you constrain the translation. So likewise, any sensitive equipment or any device you are designing, and suppose one piece you want to move it back and forth, and you want to constrain it. So suppose P, this ring is now completely constrained in one direction, and that is the translation. So this kind of designs you can make using this constraint line concept or wire flexures. Another example is like what happens if you have to suppose a cylindrical bar you have to support. So again, you have this kind of diaphragm thing. So it's like a diaphragm. And you make a hole, and you can imagine, okay, it's a 3C and 3C. You should be able to constrain it. Of course, as long as you assume that it stays in this plane, it's possible. So three constraint is possible to constrain this bar. Of course, it can rotate along this axis, right? So that's possible. But this is how you want to support it, right? You don't have to clamp it. So here you can realize that simply putting two diaphragms and can this bar can be suspended or can be supported. But here is one catch. Suppose it's a tapering. What happens at this is, this will be the force, reaction force. And what happens, they are intersecting at point M. And in this case, if you just transfer it to this one of the diaphragm, you realize that actually this force is acting at this point, and it's like creating a moment. So moment arm is there, and it can a moment can easily deflect this one. So this is not very good. It's not acceptable. So you have to be also aware of the dynamics, aware of the mechanics, any sheet flexure, how it will behave under certain circumstances. So this is going to be problematic. How to deal with that? So in that case, what you do is you just make this end in such a way that this point M lies along the plane. So you just make a contoured surface here to support it. So it will be something like this now, right? So the forces will be here, and then equivalent point M is now shifted, and it will lie on plane. And now is solved. Again, you can't make a very precise hole, so in that case you just make a triangular hole and you insert it and it will stay there. You don't have to make a precise circle. Another very good example is like whether spline shaft. Many times you use, and in heavy machinery, these are used. So it's just like 3-leg or 4-leg or 6-leg kind of thing, right? So you have a spline shaft, many splines, but can you tell me precisely like at how many locations it will be touching? So suppose if it's rotating like this, whether it's touching this surface, this surface, this surface. Yeah, because when we design, we say that, okay, all of them are transferring, right? But this is not true. This is just a hypothesis. And okay, if it's very squeezy kind of thing and very low stiffness, okay, it will just move and then start pressing. But if it's a hard material, it might be making just contact in one or two places only, right? Of course, you talk about averaging, and you say, okay, after wear and tear, it will make contact with another one. So those are the other criteria. But when it comes to precision, then you don't want to go for averaging, but you want to go for a deterministic design. You want to know exactly its touching. And in this case, what you realize that for centering of shaft with this kind of surfaces, if you have this kind of thing, so suppose just exaggerated and orange paste if you consider, and you make surfaces like this, only 3 surfaces, and suppose radially going this way, radial surface and meeting at the center, but you realize that the nature of the force you have, the nesting force, actually one nesting force is good enough, because all the directions are along the in the clockwise direction. So anti-clockwise moment will be good enough. So it will make sure that there will be contact all the time at these points. What is also important that if you start creating the surfaces, but you realize they are meeting at the surface, at the center. The center is also your thermometer. So now it may be very difficult to visualize, but if you start making it, try yourself. So just make this odd shaped piece printed, and then with the and try to assemble it. You realize that it always goes to the same place. It cannot go like this, cannot go up and down, cannot go like this, but it's centered here all the time, only one point. And so the variation is, if you really want to design something with the splines, 3 is good enough, just like this, and meeting at the, so these surfaces intersecting at the center. And what you realize, that is a self-centering. So shafts remain centered in relation to one another. So if there is any deviation, there will be some deviation at this point, but that will be fixed. So by properly adjusting these surfaces, you will be able to center it all the time. So though you see a lot of clearance here, but it's still centered because of these surfaces, not because of this cylindrical surface. So many people think, oh, it's because of the cylindrical surface, but that's not true. It's because of these radial surfaces, which is making it to centered. Every point contact has equal load also. So if there is a load, it will get distributed. So you can write the equilibrium equation and you realize that the forces are also same. So very good design, and you can compare. And in order to appreciate, what is important is you have to make it. So what you can do is you can just make it, and side you can have a little spring so that it always presses to one surface, this surface, three surfaces, and then you can see whether it's always coming to the same location. This is also a very good example, very good exercise to try. So the thermal concept of thermal center we were discussing, and I think we also talk about it. So in this case, yes, there is a nesting force, and okay, y1, y2, and x, and of course here is the intersection point is this point, so you get the thermal center there. And as in the previous case, u1, u2, u3 is there, and they are intersecting at the center. So center of the shaft or rotating member, so you will get thermal center at that point. So using symmetry to position the thermal center in the object center. So you can use the symmetry, and you can very much put it at the center, center of the shaft. So suppose if it's rotating member and you want it to be like always centered, and always, even if it's like if there is any hit source, still it's there, right? So what is said, the body is free to expand without affecting the center position. You can very much see here. So any expansion, it will happen towards u1, u2, u3, and then only point which doesn't move is the TC, the thermal center in this case. So what you can also do is you can replace these lines, the constraint lines. So these are the constraint lines. So the constraint line with the wire flexures. And what you also observe that again is a thermal center, and if there is any change in this length, right, because of temperature, it will simply rotate and readjust. The center will remain there. Likewise, you can have a cylindrical surface also, a bar constraint 3 plus 2, 5 constraint again, and it will be able to provide the thermal constraint. Of course, what you see, the thermal center is here, but it's different from the point of rotation. Instant center of rotation, they don't coincide. So that is that can give some problem. That immediately does. So another embodiment, this is the wire flexure. You can replace with the folded sheet flexure. So you just fold it, you get this kind of folds here. So folded sheet flexure embedded here already. 1, 2, 3, and then bottom 2, and then okay, you rest with the notch one. So here you have the notch sheet flexure, and then you can release one of the work constraint. So see, no rotation stiffer, okay, lower axial stiffness as there, so it can move along this direction. It's a parallel guidance, and very good example. So likewise, you can also implement it in laser welding kind of applications. This we already talked about, the V grooves in ball in V grooves. So you can, it's a kinematic support, and again you have a thermal center. Friction is a problem. So to get rid of the friction problem, you talk about this flexures. So you connect through a flexure, and that will take care of friction hysteresis part. So even if this ball is getting because of the friction, this will provide that adjustment, a small adjustment here, and that can very much work. Other problem, other solution is, okay, you get this kind of so this is like a shuttle. So you put in a flexure stage. So one bar here, and then you have a V. So another bar here. So this provides a parallel this movement. So radial movement is allowed in individual cases. So a small adjustment it can do, and it will take care of the any frictional stuff. So you can easily get rid of the hysteresis part. Again, you can design non-dismountable kinematic mounts. Kinematic mount is basically you are providing all the constraints. So again, here, suppose very simple, and simply take a sheet metal and then laser weld. So laser welding, spot welding you can do, and two spot welding, and then likewise you can get 2C by each, and then you can get 6 top. Very simple. And this is one very good example and nest of a spring. So it's a very mundane thing. I don't know whether you have seen it. It's a lamp, and that's how it holds the glass. But it's a very effective design technique, and we call nest of springs. And using this principle, so I'll come to that some other time. But even the ball bearing and or the spokes of your cycle, you can calculate, do all the calculation. Good thing is individually they are not very stiff, but altogether they can provide very large stiffness. And this concept can be used to handle optics, very optic surfaces where you don't want to touch the surface somewhere in between. So I'll come to this in later classes. So these are like lens mount you can design on the same principle. So in very high precision application, you need to hold this mirror or lenses precisely without touching the surfaces. So how you can do that? And you cannot apply very large pressure, large force. At the same time, you want a very good stiffness. So you can use this concept and design these mounts. Very good. So what we learned in this course is, so many times we say, why exact constraint design? So I think by now we must appreciate that, okay, we need a minimum number of accurate tolerances. So it's basically the reference surfaces that has to be defined well, but others can have normal tolerances, right? So we don't need very precise components. We don't need precision components or precise machining or accurate machining to design precision machines. That's one take. Another take is there is no transfer of deformation. We are not trying deformations, right? So we are like, if it's getting generated, we are removing it by selecting or designing suitable flexures. Predictable thermal behaviors, we are talking about the thermal centers, and we can very much understand what will be the thermal behavior. Even the force path is very predictable, so there is a lot of deterministic behavior in the design, and that's how we are able to control the precision. So why controlling? Because we make it deterministic so that we can calculate, and later we can compensate for that, and we should be able to achieve high precision. What we are trying to focus on is the repeatability. We are trying to get very good repeatability, and rest we compensate. So let's stop here, and um, we'll continue in the next class and start a new chapter, new topic.